All right. Well, let's go ahead and get started today. So today we're going to finish up the geology section for the course. Okay, so we're going to do lecture for chapter 12. And then that's everything that we need to cover for the midterm. Okay. Just kind of an update. I decided to go ahead and move the due date for the midterm to the 28th. Okay, I put a announcement on Blackboard that says such, and then the due date is reflected in the assignment as well, or in the midterm itself. So the 28th, by the end of the day, make sure you have the midterm completed. Okay, now that is pretty much that's the Sunday before spring break starts. Okay, so I did that for a reason. Okay, no reason to have a test languishing over spring break. Okay, got more more interesting things to do over spring break than be taking exams. So just make sure you get it done by the 28th. Okay, preferably a lot sooner. Okay, my personal thought is get it done as soon as possible after class is done today. That way it's out of the way. Okay, just make sure you've watched the videos, read the textbook, and you guys will do just fine. Okay. So I think that's it for housekeeping stuff. How many questions is the test? All right, 50 questions. Okay, you'll have plenty of time to take the midterm. Okay, so there's no need to rush it. Okay. Yeah, so also if you run into any technical issues during the test, shoot me an email, okay? It's not common, but it does tend to happen at least for one student for every test, so it's not completely abnormal either. Just know that since it is timed, if you don't finish it within that time frame, it will automatically submit it for you, okay, regardless of how many questions you have answered. Well, I suspect many of you are probably familiar with the Blackboard test things anyways. So before we get started, are there any questions on anything? Okay, I'm going to bring up the PowerPoint here.
Oh, I'm sorry. I have a question on something, but it's not about the test.
Okay, go ahead.
I was just wondering, because I took the extra credit quiz for today, and it's asked like, how old is the Milky Way? And I remember it being like saying it was like 14 billion years old, but it didn't have that option. It just had like 4 billion. Is that like is it 4 billion or 14 billion or?
I'll have to go in and look at the question. You might be thinking of the Big Bang, which was close to 14 billion. Yeah. So yeah, that would be correct for the Milky Way.
Okay.
Just slightly older than Earth itself. Okay, Earth is, it depends on who you ask, 4.6, 4.5 billion years old. So the Milky Way galaxy, which Earth is part of, is slightly younger than the galaxy itself.
Okay, thank you.
Yeah, we'll go over that in today's lecture. Okay, so we're going to talk about essentially Earth history, which is quite an interesting subject. I think you guys will get some enjoyment out of it, learn some new things. This chapter will also kind of tie up some loose ends that you might have in the back of your brains, because some things may appear to be kind of left unanswered. I think this chapter will help answer some of those lingering questions. All right, so let's go ahead and get started here. So, all right, so the Big Bang was 13.7 billion years ago. The Big Bang occurred as a result of essentially an explosion of a star, okay, called a supernova event. And the way that the theory goes is that something is made from nothing, okay, and I know that sounds absurd, but basically, before the Big Bang, it's just energy, okay? There's only energy in the universe, and there's no matter. So when the Big Bang occurs, that's when matter is produced, okay? Because energy is considered to not be considered something. It's hence when they say that it's something that's made from nothing, that's what they mean, okay? So get the explosion, and the explosion results in, there's a couple things associated with that. First is very, very rapid expansion, okay, which is still occurring today. And the second thing is that the elements that were initially produced as a result of the Big Bang were hydrogen, helium, so the lightest of the gases on the periodic chart. Okay, at that point, there was nothing material-wise present that was heavier than hydrogen and helium, okay? Now, how the materials that we have presently in the universe were created is through synthesis of hydrogen and helium. Okay, so hydrogen and helium eventually led to the creation of the heavier elements such as like iron, carbon, etc. Okay, but that was after the initial Big Bang itself. Okay, so I'm going to go back and double check this, make sure I'm correct, because I noticed the presentation says the Milky Way is 10 billion years old. So I'm going to go check, I'll check that question after class, and if it's wrong, I'll update grades for anybody that got it wrong. Okay. Okay, so before I get into the latter part of the evolution of Earth, I guess I want to break down, how we look at how we structure the universe. Okay, so we're going to go from small to big. Okay, universe is the biggest. Okay, Earth is going to be the smallest. Okay, so we have the Earth. Earth is located in our individual solar system. Okay, there's lots of solar systems. Okay, every solar system has planets and a star typically. Okay, aka the sun, which is our star. Okay, solar systems make up galaxies. Okay, and we are in the Milky Way galaxy. Okay, and then lastly, galaxies form in the universe. Okay, and the universe is really that vacuum that we call space. Okay, so that's kind of how it's structured from big to small, or small to big, however you want to look at it. Okay, we'll talk more about that when we get into the astronomy part. Okay, so back to Earth's evolution. Okay, so got the Big Bang, expansion, synthesis of initially light gases, then to heavier elements. Okay, then comes the formation of a solar nebula. Now this is a rotating cloud of gas and dust. Okay, so right here is the solar nebula. Okay, so it's a rotating cloud, okay, and what's happening is it's concurrently contracting because it's spinning in a circle, right? Because it's rotating. So it's contracting inward. And that's also resulting in the materials, that dust and dusts and gases, mainly the dust, I guess, starting to kind of clump together, okay, into larger pieces. Okay, when that all that clumping is done, okay, that you'll start to see formation of planets. Okay, so we get contraction of the solar nebula and also flattening out of it. Okay, also the material as the nebula is flattening out, the material is forming into concentric rings. Okay, with the sun forming here in the middle. Okay, so we start to get the formation of planets. As you notice in this picture, we have planets forming in each one of these individual rings, but we also have a substantial amount of debris in orbit as well. Okay, so thus, when Earth was in its early ages, very earliest ages, about 4.5, 4.6 billion years ago, what we have is essentially a molten ball. Okay, contained of all the materials that we see today, but just kind of a molten hodgepodge all mixed up. Okay. Also, because of the presence of a lot of that extraterrestrial material floating around, what we see is bombardment by some of these materials. Okay, so the bombarding materials, which I just call extraterrestrial material or debris, are essentially asteroids. That's what they're really known as. They're bombarding Earth, and they're essentially just being melted and incorporated into Earth's structure, or into its material. Okay. Now, as we move to this step here, we can see what's called differentiation is beginning to occur. So that basically the heavy materials like iron are settling out toward Earth's core, while the lighter elements and such as the gases and the silicates are essentially floating up toward the surface. Okay, so we get that separation by density. Okay, also early on in Earth's life, okay, around the time that differentiation was occurring, we get a Mars-sized asteroid essentially that crashes into Earth. Okay, so it creates a crater and ejects a whole lot of material. Okay, that material, as is typical of any body in the solar system, begins to clump together and form that ring circle. So it begins to kind of orbit around the planet. Okay, as you would guess, eventually all that material will coalesce into formation of the moon. Okay, now there's no crater left on Earth. Okay, that's because we know that at this point, Earth was still in a semi-molten state. Okay, so basically, it's like trying to put a crater in water. You know that once you take it out, the water is going to fill in to the crater. So that's pretty much what happened. You had essentially the molten material just filling in the hole. Okay, and then I guess lastly is formation of Earth's first atmosphere and oceans as well. Okay, and it's thought that the water that initially formed the oceans came as a result of outgassing. Okay, and outgassing is just simply water vapor from inside Earth that has been discharged out through volcanoes. Okay, we know from an earlier chapter that during volcanic eruptions, we get about 1 to 6% by volume gases. Okay, that's what material is made out of. And so that 1 to 6% contained a pretty substantial amount of water vapor, as well as a lot of other nasty stuff like CO2 and sulfur, but a lot of water vapor. Okay, when that water vapor was outgassed to Earth's surface and Earth's atmosphere, because of the cooler temperatures, that water vapor underwent a phase change from water vapor to liquid water, hence the water on Earth. Okay, it's also thought that most likely comets, which often have substantial amount of ice on them, probably crashed into Earth throughout the years and added some additional water as well. Okay, so that's kind of a quick look at Earth's history from the Big Bang to the initial formation. Are there any questions on anything relating to that before we move on? Okay. All right, so I just talked about outgassing, okay? And this is kind of a situation of how Earth's surface would look about 4 billion years ago. Okay, keep in mind that as late as like 4.5, probably 4.4 billion years ago, Earth was still in a pretty much molten state. So that means that by 4 billion years ago, you can see it's starting to crust is starting to form. Okay, and also these rock formations are beginning to form here. Okay, and those are called stromatolites. I'll talk about them in the next slide here. So let me just finish stuff on this slide. So yeah, I guess the only thing I didn't cover here is that Earth's primitive atmosphere. So its first atmosphere was mostly water vapor and carbon dioxide. But like I said, it could also, we know it also contains substantial amounts of sulfur, because we know that a lot of sulfur comes out of volcanoes. Okay, so not an atmosphere that was conducive for life, for sure. Okay, so by 3.5 billion years ago, okay, Earth was well into continent building, and the atmosphere was a little more starting to get a little more friendly to life. Okay, but the reason why that happened was because that's when single-celled bacteria first appeared. Okay, first evolved on Earth. Okay, now the single-celled bacteria is called cyanobacteria, and you also might just know it as blue-green algae, or just algae. Okay, so regular old green-colored algae. So the cyanobacteria photosynthesized. Okay, so it, just like what happens today with trees and plants, these cyanobacteria took in carbon dioxide, and then through the photosynthetic process released oxygen as a byproduct. Okay? So when the advent of cyanobacteria occurred, about 3.5 billion years ago, that's when oxygen itself began to become a decent component of the atmosphere. Okay, and we know that most life requires oxygen, at least animal life, oxygen for in order to survive, to live. Okay. So this is when we start to see, the composition of the atmosphere begin to change to become a little more oxygen rich. Okay, present day, the atmosphere is yet different. Okay, the present day atmosphere is about 71% nitrogen, which is an inert gas, about 20 to 21% oxygen, and then other stuff. So you can see that even present day oxygen is only composes about 1/5 of the atmospheric gases. Okay, so these cyanobacteria, or these blue-green algae, they basically form in layers, okay, over time. So you get new layers forming on top of old layers, okay, and oftentimes what you'll get too is sediments will fill in and get trapped into the filaments of the algae. And so what you'll often see is kind of alternating layers of algae, little fine sediments, algae, fine sediments, okay? And they form in these mound shapes here, okay? So each one of these layers represents an older layer that was put down before the newer layers, okay? So the newest layers are up here. This is basically a side view looking at a stromatolite. It's kind of like cutting through a stromatolite and looking at the layers from the side. Okay, this picture over here are stromatolites. They look kind of like rock balls, essentially. Nothing fancy, but if you cut into them, you would see the layering. They're not very common today, but they are present. Okay, they're stromatolites. They are still living. They did not go extinct. They just don't. They're not prevalent as they once were. Okay. So the key with stromatolites is that they were the first life to photosynthesize, okay, and that photosynthesis is what led to production of oxygen in the atmosphere. So very important. All right, so now we're going to look at Earth's history in chunks of time, okay? So in this chart here, you can see that time on Earth is broken down into very large chunks called eons. Eons are broken down into smaller chunks called eras. Eras are broken down into smaller chunks called periods, and et cetera, it keeps going. We're more focused on eons and eras, though you've probably heard some of these periods, like the Jurassic, of course, with the dinosaurs. But we're going to focus mainly on the eons and the eras in this presentation. Okay, so first we're going to start out at the very bottom with what's called the Precambrian era. Okay, this chart here is not to scale, okay, but this one over here, this kind of pull out one, this is to scale in terms of time. So Precambrian includes about 88% of Earth's history, so the lion's share of Earth's history, and then the remaining 12% is included in what's called the Phanerozoic eon. That's where we currently, that includes present day. Okay, so present day, we live in the Phanerozoic eon, the Cenozoic era, the Quaternary period, and in the Holocene epoch. Okay. All right. So that's kind of how that works. You can see that Precambrian gets broken down into other subcategories, but I'm not going to worry about those for this class because not a whole lot was actually going on during the Precambrian. Okay, pretty much what was happening was continental accretion, so basic formation of Earth's crust. Okay, and to kind of extrapolate on that, the crust that was created during this time frame was what makes present day tends to make up the cores of our continents, or the oldest pieces of crust in the continents. Okay, so how those chunks of rock essentially formed, or how they resulted in creating continents, was through collision. So we know that just fragments of crust would be created, okay, and plate tectonics was pretty much started right away, and all these materials would get they would collide with each other and become amalgamated into larger chunks. Okay, and that process still happens today. Okay, so to kind of recap, Precambrian pretty much extensively associated with continent building and just the presence of single cell bacteria at that point. So not a lot. Okay, here you can see the original land masses that were formed during the Precambrian and actually Phanerozoic. So anyway, well, here let me explain it. Okay, so the red circles represent the oldest known rocks, period, in the world. Okay, and you'll notice that those red circles are surrounded by brown colored rocks, which are the next oldest rocks. Then the brown ones are surrounded by yellow, which are a little bit older. Younger rather. Sorry, I said that wrong. The red is the oldest. The brown is the next youngest. Yellow is the next youngest after that, and then finally the green color is the youngest. Okay. So what you can see is, especially with like North America, the stable interior of the continent. So Minnesota, Wyoming, this one up here, you can see are the oldest rocks in the continent. Okay, and those areas are called cratons. Basically, the oldest, most stable area of continents. Everything that formed after that essentially just was added to the edges of that craton through the process of accretion. Okay, and if you'll notice, the youngest rocks, which are green, initially the west coast of the U.S. would have been somewhere around Nevada, Utah state line. Okay, so you can see that a substantial amount of land area has been added to the western U.S. and then also to the eastern U.S. as well. Pretty much the Appalachians and east are also the youngest rocks. Okay, so Midwest and this area called the Canadian Shield up here in Canada, those are the absolute oldest areas of North America. All right, so over time, as I mentioned, these crustal fragments will move around and they'll occasionally crash into each other, okay? And they'll amalgamate, okay? Sometimes they don't necessarily fully amalgamate, especially the bigger they get. And that brings me to the concept of the supercontinent. Okay, so the bigger that the continents get, basically what happens is they will crash together. Okay, so plate tectonics is driving them around just as what happens today. So they'll crash together, and they'll pull apart, okay? And that process still goes on today. Okay, so there were two main supercontinents in Earth's history. Okay, the first was Rodinia about 1 billion years ago, and then the newest one was Pangaea, which was around 500 to 200-ish million years ago. And basically, yeah, supercontinents were formed, all the continents were smashed together, and then they were later pulled apart as a result of plate tectonics doing what they do. Okay. Okay. One major thing that occurs as a result of the supercontinent cycle is when these continents smash together. Oftentimes, that'll result in mountain building. Okay, and just by merely smashing together, they're just driving the land upward. Okay, and during these events, mountains such as the Appalachians and the Caledonian Range in the British Isles were essentially produced as a result of these smashing together during the supercontinent cycle. Okay, so now let's shift gears here, and we'll take a look at the Phanerozoic. Okay, this is where pretty much everything else that you know of happens. Okay, so the Phanerozoic is really broken down into 3 different eras. Paleozoic means ancient life, so that's the oldest. Mesozoic means middle life. Cenozoic means current life, something like that. I forget exactly what Cenozoic stands for. But we are currently living in the Cenozoic era. Okay. So now let's go ahead and break down what happens in the Phanerozoic by age. Okay. One important thing that I want you to want to point your attention to is this line here that separates the Precambrian from the Phanerozoic. That is at 542 million years ago. Okay, that's a very important date in geologic history, and obviously it's very important because it's the dividing line between 2 major eons. What happened there was an explosion of life. Okay? It's not entirely well known what drove that process, but there was a mass explosion of life. What's the term they're called? They call it the Cambrian explosion. Okay, so at that point, evolution is going from multicellular organisms, single-celled organism to multi-cell organisms. Okay, we'll start out with the Paleozoic here. So the ancient life, the oldest time frame. So as I mentioned, right around that 542 million years ago marks that explosion of life. Okay, and that explosion of life, it didn't take very long before hard parts were created for life. Initially, the life that formed right at the beginning of the Paleozoic was essentially sea-dwelling animals that were invertebrates. Okay, so they didn't have bones or shells. But as you can imagine, that's not very conducive to survival. So during the early Paleozoic, what resulted was the advent of hard parts. Okay, and hard parts, I mainly mean like shells. Okay, not bones at this point. Bones appear a little bit later, but hard parts for invertebrates. Okay, so basically we get calcium carbonate shells. Okay, so calcite shells that are pretty durable that protect these invertebrates. Okay, kind of like how a shell protects a turtle present day. Okay, at that point, life was just specifically restricted to the oceans. Okay, and like I said, they were only invertebrates. Okay, so types of things that you would see during the early Paleozoic would be mollusks, sponges, corals, trilobites, and then a host of invertebrates as well. But these little kind of bug-looking arthropods are called trilobites. A lot of people have fascination with trilobite fossils. They're interesting. Okay, so moving on toward the mid-Paleozoic, okay, life continues to diversify and evolve. Okay, so initially, what's present is the lobe-finned fish. Okay, and this is where bones start to, evolution starts to result in the formation of bones. Okay, so lobe-finned fish, we know they have fins, right, to move. Okay, part of that is a bony structure. Okay, during the mid-Paleozoic, lobe-finned fish evolved into early amphibians. Okay, and here you can look at the evolution of the bone structure from the fin to the leg during the mid-Paleozoic. Okay, so pretty interesting. Okay, and then more toward the later Paleozoic, during a time frame called the Carboniferous. Let me go back and show you where that's at. Right here. Okay. So the Carboniferous is a period, and it really gets broken down into two subcategories that are still considered periods. Okay, so it's a little bit confusing, but the Pennsylvanian and the Mississippian periods, when you combine them together, they're generally referred to as the Carboniferous. Okay, so Carboniferous is an interesting point in time because at that point there was a supercontinent that was centered on the equator. Okay, and because we know that the equator is warm, very moist, has a lot of plant growth, we know that it was very swamp-like or had a lot of wetlands, rainforest type situation. Okay, so so this goes back to our discussion about how coal forms. Okay, so coal forms from a lot of plant material dies, falls down, gets rapidly buried. Okay, and then it eventually turns into coal over time with pressure and a little bit of heat, not much, but mostly pressure. So we get the formation of coal during the Carboniferous era, okay? And that was the only time in history when coal beds were formed. Okay, so that's a very unique time in Earth's history. Now, at the end of the Paleozoic was a mass extinction event, okay? And at this point in time, about 90% of marine organisms went extinct. Okay, so that's a lot. And about 70% of vertebrate species on land went extinct as well. But there weren't a lot of vertebrate species on land at that specific point in time. Okay, that came a little bit later. So 90% of the ocean species at that time. So what a mass extinction does is it gets rid of a lot of the species. So it basically, so that the remaining species that did not go extinct, they are now introduced to a world where they have ample space, probably a lack of predators, okay, and a lot of resources available at their disposal because everything else died. So they just find themselves with this major advantage, okay, and that typically results in the survivors rapidly evolving. Evolution tends to speed up during that situation because the survivors pretty much have run of the house, okay. Okay, before I move on to Mesozoic, are there any questions on the Paleozoic or the Precambrian? Okay. So Mesozoic, let me roll back and show you where that's at. So Mesozoic is right here, this kind of darker blue or mid blue here. Mesozoic includes the Triassic, Jurassic, and Cretaceous periods. Okay, it's also known as the Age of Reptiles. Okay, you'll see that as we transition from late Paleozoic to Mesozoic, and partly as a result of the mass extinction, we see that the dominant species go from amphibians to reptiles, okay, of which dinosaurs are. So some important geologic events of the Mesozoic era. Okay, the formation of Pangaea, that last supercontinent, okay, which you're seeing here, its process of formation and then breaking up over time. So Pangaea formed as a supercontinent, and it resulted in the formation of the Appalachian Mountains. And formation of the Appalachian Mountains. Okay. Also, during the Mesozoic was a time where a lot of land area was essentially smashed onto the western coast of the U.S. So a lot of land area was added during the Mesozoic as well. At the tail end of the Mesozoic, that's when we see the formation of the Rocky Mountains. Okay, as I mentioned before this time frame. Okay, so during the Paleozoic, essentially the west coast of the U.S. was around where Nevada and Utah meet. Okay, so it's thought that there was a convergent plate boundary there at the coastline, as there is present day up in the Washington and Seattle area, or Washington and Oregon area, rather, with the Cascades. So there's a subduction zone there, and it's thought that that subduction zone is what created the Rocky Mountains. Okay. There's still quite a bit of debate amongst geologists if that really is true or not. You would think it would be clear cut, but it's actually formation of the Rockies is actually kind of a touchy subject with geologists even still today. But that's at least kind of the most accepted school of thought for how the Rockies formed, and it makes sense, okay, because we see the same thing happening with the Cascades today. All right, so life in the Mesozoic. As I said, age of reptiles, so we get that transition from amphibians to reptiles. So, after the end of the Paleozoic extinction, organisms that did survive, as I said, they ended up diversifying. Do we have a question here? Okay, what is the name of the era that's present today? Okay. Let me go back to that slide and I'll show you. Okay. So present day, we're in the Phanerozoic eon, the Cenozoic era, which is the question that was asked. Okay, and then it gets boiled down from there. So technically, geologists refer to present day as the Holocene. Okay, that's the epoch. It's kind of the smallest time frame that geologists measure things with. Okay. You might also be familiar with Pleistocene, which was the epoch right before Holocene. That's the Ice Age. Okay. Ooh. Yeah, here we were. All right, so Mesozoic. Okay, this is the time frame in which plants that produce seeds evolved and became quite dominant. So mainly, pine trees. Okay, those are referred to as gymnosperms, plants that produce seeds. Okay, also things like sunflowers, of course, those are gymnosperms as well. Reptiles became the dominant land animals. Okay. Initially, reptiles were smaller, okay, during the early Mesozoic. But like I said, in the situation where you have a mass extinction, that kind of allows evolution to speed up. So the natural trend is for small animals that do survive, and typically the ones that do survive are the smaller animals. Okay, you'll see that again in the Cenozoic. The small animals survive, and then they relatively quickly evolve into larger sizes through different lineages. So these first reptiles were small, but then they, of course, got quite large by the mid-Mesozoic because that's when dinosaurs became very dominant. So I probably don't need to lecture you guys on dinosaurs. That's probably the most well-known geologic concept by most people in society. But basically, you have two types of dinosaurs. You have herbivores and carnivores. Okay, the herbivores tend to be larger in size, and they often have long necks. That's how you can tell which ones are often herbivores. Carnivores tend to be actually smaller and not have that long neck. And then there was also like a flying dinosaur called the Archaeopteryx. This is thought to be the ancient ancestor of modern birds. Okay. So at the close of the Mesozoic, late Mesozoic, right around 65 million years ago, what happened was an extraterrestrial object, quite large in size, so basically an asteroid, came through Earth's atmosphere and crashed down into the Yucatan Peninsula in Mexico. Okay. And what that did was two things, basically. Okay, one, since it was such a huge object, when it hit the ground, it created a shock wave, and concurrently created a lot of heat. Okay, so anything within a certain radius of that crater would have been initially killed by either the shock wave or the heat. Okay, what wasn't initially killed, that life had to deal with what's called nuclear winter. Okay, because that asteroid essentially, when it hit the ground, it spewed up a whole lot of dust into the atmosphere. Okay, and that dust, which is very fine in size, stayed entrained in the atmosphere for a long time, for several years. Okay, and that wreaked havoc on plants. Okay, because a lot of the sunlight was being blocked out, very little was actually making it to Earth's surface. Plants were also a lot of plants were going extinct. Okay, and as you can imagine, with such large dinosaurs, you had the herbivore ones no longer had much plant material to eat because of this nuclear winter that was occurring. Okay, so the herbivores were the first dinosaurs to die off, provided they survived the initial shockwave. And then, of course, once they died, then the carnivores didn't have anything to eat, so they died off as well. Okay, so in terms of the dinosaurs, it's often misunderstood that they all died as a result of the asteroid, why am I blanking on this? The asteroid hitting Earth. Okay, that's not entirely true. A lot of life survived that, and that life tended to be far away from it geographically. But that nuclear winter is what did the rest of them in. Okay, the dinosaurs especially. They lost the food source and then they just died from starvation. All right. So with the dinosaurs out of the way, these huge, very large reptile-like animals, that paved the way for evolution of um, smaller reptiles and also small mammals. Okay, small mammals were present during the late Mesozoic, during the dinosaurs time age. It's just that those mammals were more rodent-like at that point. Okay, so mammals and dinosaurs did coexist together at the same time. Mammals survived as did small reptiles. Okay, and then that ends the Mesozoic, and we now move into the Cenozoic. Okay, so the mass extinction, just like what happened in the past with the actually it happened 5 times in the past. I didn't cover all of them, but just so you know, there were a total of 5 major extinction events in Earth's history. We saw the same exact thing where you get all the predators and big animals out of the way, they all die, and the little guys come in and they start to diversify because, again, they don't have predators and they have all this abundance of resources and area, land area to survive. So the early Cenozoic really was resulted in the mass evolution of mammals. Okay, so especially from small mammals to large mammals. Okay, and we've seen that before, right? From small to large, happened with essentially with the dinosaurs. Okay, after the Paleozoic extinction, we initially started out with smaller reptiles, and then they evolved up to dinosaur size by the end of the Mesozoic. Okay, same thing here. Started out with small mammals, and they've evolved up to larger size mammals. Okay, so mammals evolved into 2 separate groups: the marsupials and the placentals. Marsupials, of course, are mammals that carry their young in a pouch, such as a kangaroo. Marsupials were on a separate evolutionary track as a result of the breakup of Pangaea. Okay, basically islands like Australia became separated from the main continental areas, and the mammals at the time evolved into marsupials. Okay, now most areas of the continents have placental. Okay, and that is essentially a liquid material that carries nutrients, food, and also wastes for a growing fetus. Okay. And also during the Cenozoic was the evolution of flowering plants. Okay, those are called angiosperms. Okay, when angiosperms began to diversify, that also resulted in a very quick and massive diversification of bird species, okay, which makes sense. There's a symbiotic relationship there. Okay, so what you're looking at here is a kind of a recap of what I call lineages, okay, or different lines of species, basically. Going from the Devonian, okay, that's the middle of the Mesozoic, up through present day. So what you can see is all these modern forms of animals evolved from lobe-finned fish. Okay? And you may not know that. It's thought that humans evolved from lobe-finned fish, which, by the way, lobe-finned fish, actually everything initially evolved from cyanobacteria. Okay, that's like the ultimate ground zero there. Okay, so it goes back further than lobefin fish, but as you can see, different lineages split off from lobefin fish. So we get amphibians, and then we get another split off that turned into early reptiles. Okay, early reptiles then split into mammal-like reptiles and present-day reptiles like snakes, turtles, etc. Okay, now going up the mammal-like reptile lineage here, okay, those mammal-like reptiles evolved into early mammals, okay? And again, initially they were thought to be relatively on the small side. Okay. Now, when I talk about evolution here, I want you guys to understand that evolution itself is kind of misunderstood. So oftentimes, you'll hear people say that humans descended from apes or monkeys, whatever it was. That is kind of a technical misnomer. People think of evolution as like a parent-to-child type evolution. So parent has child, child has child, etc. That's how the lineage keeps going. That does happen, yes. But how lineages begin to split off to create a separate track, think of it as like a cousin, okay? So humans really aren't an ancestor. Our ancestor isn't necessarily the ape or the monkey. The monkey's more like a cousin to us, okay? Because there was that lineage split off right at the monkey to, I believe, what would have been the hominid or Homo sapien, early humans, okay? So yeah, think of evolution as two separate tracks. One can be the parent, child, their child, and so on, and then also that splitting of the lineage as like being a cousin. Okay. All right. And so this is just this kind of a recap of the most important things that have happened throughout Earth history. The oldest is up here. The youngest is down on the bottom. I didn't cover all of this, okay, but it's worth spending some time after class to go through and look at this, because there are you'll notice some really interesting ones in there, such as, for instance, the first horses. Who would have thought that the first horses were actually dog-sized, okay? And they didn't initially have hooves, they had paws with pads and whatnot, like dogs do, okay? The environment changed, the climate changed in the early Cenozoic to the point where it was a little bit drier and grasslands began to form. Okay, so grasslands we know have higher grasses. So there was that evolutionary need for these small early horses to evolve so that they could see over the tops of the grasses in the grassland in order to protect themselves from predators. Okay. So you can see there's many instances of things like that, okay, that occur in Earth's history. Very, very interesting and unique. All right, I think that's it. Yeah, so that's it for this lecture. Are there any questions on anything that we've covered today? Okay, hearing none, we'll conclude that, and we're just going to keep trucking right along. So we're going to actually start oceanography next Wednesday. So you'll be kind of juggling the midterm and are moving on to oceanography. That's why I say try to get the midterm done as soon as possible. That's in your best interest. But yes, make sure when we resume for class next Wednesday, the 22nd, that you read chapters 13 and 14 and watch the one video. So lucked out there, one video associated with that first lecture. So, all right, well, then that's it. So we will conclude for the day, a week rather. And you guys enjoy the weekend. It's going to be a nicer weekend again, so enjoy that. And then I'll see you on next Wednesday.